In the last video, we ended with the LaGrange remainder. And I was telling you that the next derivative in the polynomial, or the next term in the polynomial, will be equal to the amount that we are off from the actual value. So if we're plugging in a value to our polynomial in order to estimate the function, we know that the remainder will be the next term at some value z. And this is where things get weird. Because z, we know, will be between what we're centered at and what we're plugging in, but we don't know exactly what that value is. So that makes this really difficult to find. So what we're going to do in this video is we're going to estimate what that value might be. So we're going to look at, this was the LaGrange remainder, like this is exactly what we are off. But what we're going to do today is find a range. So we're going to say that we think that the value of the function is this, plus or minus a little bit. So we're going to give kind of a confidence interval, if you will. So let's recap kind of where we've been. And we're going to look at Taylor's theorem. Taylor's theorem, we've talked about this part before, that the actual value of the function is equivalent to plugging the number into the polynomial we come up with, plus the exact remainder. And that makes sense. However much we're off, plus our estimate will equal the exact value of the function. So what Taylor has done is he has summed this up in notation, in a symbolic way. So he has used sigma notation to write out the Taylor polynomial that we've been discussing so far. So if we use 0 and put it in for k, that's saying the 0th derivative, or the original function. So that's f of a over 0 factorial times x minus a to the 0. If we plug in 1 then, that's the first derivative, so f prime of a over 1 factorial, x minus a to the first. If we plug 2 in for k, that's the second derivative, so f double prime of a over 2 factorial, x minus a squared, and so on. That's that general Taylor theorem, or Taylor polynomial, we have been discussing so far. And then if we add on this remainder, then we know that that will be the actual value of the function. But we're going to talk about this part. This part is the part that throws a little wrench in the works. So what we're going to do is find an error bound. So because finding that the next derivative at some z is difficult, if not impossible, we're going to approximate that value. We're going to choose a convenient value, just like we chose a convenient value to center our function around in order to write the polynomial. We're going to find a convenient value to approximate that next derivative at z. So if we can find a convenient value, we call it m, such that m is greater than the next derivative at z. So if that value m is greater than the next derivative at z, then we can guarantee that the remainder will be definitely less than this expression. So the only difference between this and the Lagrange remainder is we took out that next derivative at z and replaced it with m, and m being our convenient value that we can evaluate without a calculator. Let's see if we can talk about this a little more, because right now this is all very theoretical. Let's see if we can start to think about it and put it into play. So let's go back to the graph we had of e to the x and the polynomial that we chose to match e to the x. So what the Lagrange remainder says is that we have some value z here, then we know that there is a point in here such that f, the next derivative at z over n plus 1 factorial times x minus a to the power of n plus 1 will indeed equal that next derivative. I mean that remainder, what we're off by. So what we're saying here, what the Lagrange error bound is saying is, since we cannot find this exact y value, we're going to choose a y value that is close, but definitely bigger than that one in order to estimate the remainder. And what you choose m to be is, for the most part, up to you. However, we want to try to choose a value of m that is close to the area we're working around. Just like when we were writing the polynomials, the further away we get from the center, the worse our estimate is going to be. So we want to choose values of m that are relatively convenient. And for the most part, you can choose just about anything you want, but there are some standards to this. So let's stop talking theoretically. Let's see if we can try to put this in practice. So I'm going to give you an example here. There are two parts to this. The first part you can do right now. The second part we're going to do together. So I want you to use the third order Maclaurin polynomial for sine x to approximate the sine of 1/2. So please go do that without a calculator and come back. Okay, so let's write this third order polynomial. Actually, I'm going to write this in a very sine x is approximately the third order polynomial, which is x minus x cubed over 3 factorial. Notice that the equivalence and then the equal sign. So I'm saying sine x is equivalent to the third order polynomial, and the third order polynomial is equal to x minus x cubed over 3 factorial. So now we can use that to estimate the sine of 0.5 or 1/2. So I'm going to do that by plugging 1/2 into this polynomial. All right, let's simplify this a little bit. 1/2. 1/2 cubed is 1/8. 3 factorial is 6. 1/2 minus 1 over 48. Getting a common denominator then, this would be 23 over 48. So our third order polynomial gave us a value of 23 over 48, which is approximately the same as the sine of 1/2. But we're off. That's not the exact value of the sine of 1/2. So what we're going to do now is try to figure out, okay, we think it's 23 over 48 plus or minus a little bit. So let's go see if we can find that little bit. All right, so if we look at this, we know then that the next term in the polynomial will be the remainder. And using the LaGrange error bound, we're saying that this remainder will be less than or equal to some convenient value m, we'll talk about that in a second, over 3 plus 1 factorial times x minus a. X was the value we plugged in, a was the value we centered around, and that's to the power of 3 plus 1. Okay, let's keep going. Let's simplify this a little bit. We'll talk about m in just a moment. So we've got 3 plus 1 factorial, that's 24. 1/2 to the 4th is 1/16. So we're saying that the remainder, the amount that we're off from the actual value of the sine of 1/2, will be less than or equal to some value m, we'll find that in a second, over 384. Let's talk about this m value. Remember, m needs to be some convenient value that is greater than the next derivative. Okay, the next derivative. So in our case, the next derivative would be the fourth derivative. So let's find that fourth derivative. F of x was sine x. I'm going to move this over so I have some more space. F of x is sine x. F prime of x is cosine x. Second derivative is negative sine. The third derivative, negative cosine. So now the derivative we're really concerned about here, the fourth derivative, is the derivative of negative cosine, which is back to sine again. So what we're trying to say is we want m to be greater than or equal to the sine of some value z. Okay, let's look at this graphically. I think that's going to make this be a little bit better. So we're trying to find some value m that is greater than the sine of some point z. All right, I stored this graph over here for later, and later is now. So I'm going to expand this graph so we can look at it a little bit closer. This is the graph of our third order polynomial. This is the graph of sine x. We centered our polynomial about 0. So here's the a value. We are trying to find the sine of 1/2. So here's the x value. We know that somewhere in between a and x, there is some value z, such that if we plug z into the next term, we'll get the exact remainder. So what we want to find is some value for m, some convenient point that is greater than this y value. Because remember, the fourth derivative was sine x. So this point right there is the fourth derivative at z. We have many, many choices on this sine x function. So for m, I mean, this is where it gets a little bit strange because we're trying to just choose a convenient value for m. Rule of thumb is when we are working with a sine or a cosine function, the rule of thumb is that the convenient value for m is 1. Because I know that 1 is the highest the sine function will go. So 1 will definitely always be greater than or equal to the next derivative. Always. So the rule of thumb is to choose 1 as the value for m. And this looks like it's about 1 right here. We could have gotten a point that's closer because I know that pi over 6 is in here somewhere. And pi over 6, the sine of pi over 6 is 1/2. And so I know that that value 1/2 is also greater than that fourth derivative at some value z. So I have two choices for m. And honestly, it's up to you which one you choose. But if we're talking about convenient values and trying to estimate these things without a calculator, using m as 1 is definitely more convenient. But we'll look at both of them. All right, so where we left off was we were saying that the remainder is less than or equal to whatever value we chose for m over 384. So let's go play around with that a little bit. So the remainder for plugging in 1/2 is less than or equal to, and I'm going to do both of them. I'm going to choose 1 over 384 or I'm not sure why I decided to put parentheses around the 1/2, but that's okay. Or 1/2 over 384, which would be 1 over 768. So what we're saying is the answer we got from up above, the estimate that we got in part A, and the estimate we got from part A is 23 over 48. So what this LaGrange remainder is saying, or this error bound, is saying that if we have the sine of 1/2, that's what we were trying to approximate, we know that this value of sine of 1/2 is somewhere between 23 over 48 plus 1 over 384 and 23 over 48 minus 1 over 384. This is the error bound. Or if we got a little more exact even, if we chose 1/2 for m, it would be plus 1 over 768 or minus that. So let's do some actual calculations now and see if we were right, if we are actually in between those bounds. So if I do 23/48 minus 1 over 384, I get 0.474765625. And then if I do 23/48 plus 1 over 384, I get 0.48. I get this value. I'm going to move my other estimate, my other error bound, down a little bit further. And now if I actually calculate the sine of 1/2, I'm going to use a different color for that one. If I actually calculate the sine of 1/2, I get this. .4794255, so on and so forth. So we were right. Our estimate was between those two values and we were correct. Okay, now let's check it. What if we got a little bit more precise with our value of m? In other words, we chose a point that was a lot closer. Let's see if we were also correct there. So I'm going to do the other side first. 23/48 minus 1 over 768. It's 0.477. 8645833. And then if I do 23 divided by 48 plus that, so it kind of depends on what you're trying to do here. If we're trying to build a spaceship or a space shuttle, we'd probably want to get a little bit more accurate with our m value and choose the value of m that's closer to what we're working with. Because I can see here in my second set of numbers, my range of values was much more narrow. And I was still correct because the actual value of sine came in between those two. Okay, this is just an introduction to finding the LaGrange error bound, and m is a little bit strange for right now. In the next lesson, we're going to spend a lot more time looking at other values for m and how to find that